All right, everybody, I'm glad to have you here, and I've got a terrible joke for you today. Why did the fraction break up with its decimal equivalent? You'll have to stick around until the end to find out. Your objective in this video is to explain why the sum and product of rational numbers is also a rational number. Noticing patterns among different groups of numbers is an important part of mathematics. For example, whenever we add two counting numbers, the sum will always be another counting number. Let's look at example 1. 7 and 5 are both counting numbers, and when we add them together we get 12, which is also a counting number. However, sometimes when we subtract one counting number from another, we get a counting number, and sometimes we don't. Here we're going to look at examples 2 and 3 to see when that happens. 9 and 3 are both counting numbers, and when we do 9 minus 3 we get 6, which is also a counting number. 2 and 7 are counting numbers, but when we do 2 minus 7 we get negative 5, which is not a counting number because counting numbers only go 1, 2, 3, 4, 5, and so on. This is an integer, but it's not a counting number. So sometimes when we subtract one counting number from another, we don't get another counting number. The rational numbers are said to be closed with respect to addition, subtraction, multiplication, and division. This is a fancy way of saying that whenever we add, subtract, multiply, or divide two rational numbers, we will get another rational number. It'll be helpful to look at some examples and the general explanations as well. Let's start by multiplying two rational numbers together. In example 4. 7. And remember, when we multiply fractions, we multiply across the denominators. So what we're going to get is 2 times negative 5 in the numerator, and we multiply across the denominators 3 times 7 in the denominator. So this will be negative 10, because 2 times negative 5 is negative 10, over 21. And we have a fraction now, negative 10 over 21, which is a rational number because our numerator is an integer and our denominator is an integer, so it fits the definition of a rational number. Now for the general case, we need to remember the definition of the rational numbers. They are the set of numbers a divided by b such that a and b are in the set of integers and b does not equal 0. Because the notation can be a little tricky, let's have another look at how we represent that set. Remember that the rational numbers is that set of numbers a divided by b such that a and b are in the set of integers and b does not equal 0. So any number that fits that description, that definition, is a rational number. Since we will need to consider two rational numbers, we can also say that c divided by d is a rational number if c and d are in the integers, or we represent that as z, and d does not equal 0. Now, when we're going to multiply these two fractions, a over b times c over d, we multiply across the numerators, a times c, and we multiply across the denominators, b times d. Now, ac, because a and c are integers, a times c is an integer. And b times d, because b and d are integers, b times d is also an integer. So we have one integer divided by another integer, so this does fit the definition of a rational number. Notice that this relies on the fact that when we multiply two integers, the result will also be an integer. When it comes to the sum of two rational numbers, it's a bit more complicated, so a specific example will be especially useful here. We're going to look at that in example 6. All right, now when we're adding two fractions that have different denominators, we need to rewrite those two fractions so that they are written in forms with equivalent denominators. So I need to change the way this looks without changing its value, changing the way that this looks without changing its value. So we're going to multiply each fraction by a special form of the number 1. I'm going to multiply this first fraction by 5 divided by 5. So I'm going to multiply that by 5 over 5. That is a special form of the number 1. And then I'm going to take this 3, the denominator from the other fraction, and I'm going to multiply 2/5 by 3 over 3. So that is also a special form of the number 1. So we're not changing the value of these fractions, we're just changing the way that they look. So here I have two fractions that I need to multiply. 5 times 1 is 5, over 5 times 3 is 15. So what I'm saying is that this 5/15 is equivalent to this 1/3. It just looks different. And now we have our addition. And so we need to multiply these two fractions. 2/5 times 3 over 3 is going to be 6 over 15. And now that we have common denominators, we can add our numerators. 5 times 6, for 5 plus 6, 5 plus 6 over 15 is equal to 11 over 15. And that is how we add those two fractions. And the real key here is that this is a rational number. So we started out with two rational numbers that we were adding together, and the result was another rational number. The key to example 6 and its generalization, example 7, is that we must multiply the first fraction by the denominator of the second fraction divided by itself, and multiply the second fraction by the denominator of the first fraction divided by itself. All right, in this example, we're going to very much follow the pattern that we did in the previous example, where we have our two denominators that are going to help us to rewrite these fractions with common denominators. So we're going to multiply a over b times d over d, and we're going to multiply c over d times b over b. And the result is going to be, so when we multiply these, we're going to get the fraction dA over dB, because I'm multiplying the dB and the dA there. And then we're going to be adding to that, multiplying these two fractions. We're going to multiply CB over D times B, and so that's going to be over dB. And notice that now we have common denominators, or the same denominators. So now we can just add. So that's going to give us dA plus CB over dB. Now this probably feels pretty confusing. These kinds of general explanations can be. But the real key here is to remember that since D and A were both integers, D times A will be an integer. Since C and B were both integers, C times B will be an integer. So we're adding two integers together, which means the entire numerator will be an integer. And then since D and B were both integers, D times B will be an integer. So the denominator is an integer. So we have a fraction where the numerator and the denominator are integers, which means this is a rational number. So we are adding two rational numbers together, and the result is a rational number. This last example does rely on two facts. Number one, the product of two integers is an integer, and number two, the sum of two integers is an integer. Okay, here's that joke again. Why did the fraction break up with its decimal equivalent? Because it kept repeating itself. Have a great day, everyone. Be well.